In this lecture, we'll be talking about a particular class of non-linear systems, namely second-order systems. Okay. To be precise, second-order autonomous systems. So, according to our notation, we'll be talking about this case, general x equals f of x, where the state vector is of dimension 2, or of size 2. X is x1, x2. Okay. On the plane, R2 real plane, and therefore f must be a mapping from R2 to R2. Okay. Or we can write down individual equations. Okay, so x is x1, x2. So x1 dot is f1 of x1, x2, and x2 dot must be f2 of x1, x2. So we have f1, x1, x2, and x2 dot is f2, x1, x2, where this vector x1, f1, f2, x1, x2 is no other than our mapping from R2 to R2. Okay. Now, why study second-order systems? Why not study first order? Well, the reason is that, well, we could have see a few examples on first order systems, but since the order is just unity, we cannot see much interesting phenomena if the order is 1. But once you increase the order to 2, all of a sudden, the richness becomes apparent, and we see a lot of phenomena, a lot of different behavior, which can be seen also in higher order systems. Okay, so that's one of the main reasons, because studying second order systems or having a qualitative understanding of second order systems is helpful in order to understand what's going on, what could be going on in higher order cases. Okay, also, and perhaps this is even more important. One benefit of studying second-order systems is that the solutions involve on the plane, okay, and that means we can draw it on the board, on the paper, or we can simulate it and see it on the computer screen. Therefore, we can visually understand the entire dynamics. Okay, so that's therefore that's a strong motivation. Okay. Why study second-order systems? Because we can visualize the trajectories or solutions, so that we can understand the general behavior of different systems. And even though they're not as simple as, obviously, first-order systems, they're still simple, and therefore it allows many tools to be applied in order to analyze them. Okay, so simple enough to study in detail. Okay, and even though they're simple, they're not too simple to be interesting. A lot of, as I said, a lot of interesting phenomena can be observed through different dynamics, second-order dynamics, and such phenomena, examples allow us to understand, to some degree, the more complicated phenomena that appears in higher-order systems. Okay, yet rich enough to be be useful in understanding higher order cases. So, before we see, well, under this title, what we're going to do, we're going to see some examples, and what we will have a rough understanding of what can be encountered with the second order system, and also we will point out an important theorem that that tells us certain things about second order systems, which is the Poincare-Bendixson theorem. Okay, unfortunately, it doesn't have a direct generalization to higher order systems, but for second order systems it's quite a nice check for a periodic, whether the system has or displays a periodic orbit or not. Okay, so let's introduce some definitions first. Let x of t be the solution of our differential equation, okay, or the system x that equals f of x. Now, by x of t, we mean, since we're talking about second order systems, we mean this vector, okay, the first entry, the first state variable, second entry, second state variable, and this vector, the entries of that vector, changes with respect to time. So therefore, if also we describe this vector as a point on the coordinate system that we draw on the board, then as time goes on, these two coordinates change. Therefore, the point that describes or represents the state at some given time also will be moving along on the plane, okay, on the board. The solution of x that equals f of x, our second order system, starting in initial condition x naught in R2, that is x at initial time. Since the system's time invariant, we can take initial time anything we want and without loss of generality. Therefore, we will take initial time to be 0 for notational convenience. Okay. x0, the value of x at t equals 0 is this x sub 0. Okay. Now, the collection of points, x1t, x2t. Now for each t, we consider this pair as a coordinate on the plane, and that is a point on the plane, and as time goes on, that point will move around, okay? And the collection of all those points for future time on x1, x2 plane is called trajectory. Okay. Or orbit of the system. Okay. Now we will provide many examples to such trajectories. The plane that we display those trajectories on is called the state plane, or sometimes a phase plane. The x1, x2 plane is usually called the state plane or phase plane. Okay. let us take a simple example. In fact, one of the simplest examples, it would be an LTI system, and apply or see what these definitions or concepts correspond to for that case. Here is our first example for a second order autonomous system. So let the dynamics be given as x1 dot equals x2. So this x2 is our f1 of x, and x2 dot equals f2 of x, and f2 of x is minus x1. Note that this is a second order linear system. Therefore, we can write it in x that equals a x4, where a is the 2 by 2 system matrix. Okay. So therefore, this implies that x is x1, x2, therefore x dot is x1 dot x2 dot vector equals some matrix times the vector x1, x2. And the entries of this matrix is coming from these two equations. Okay? So x1 dot is 0 times x1 plus 1 times x2, and x2 dot, the second row, is minus 1 times x1 plus 0 times x2. Therefore, this matrix is our A matrix. Okay. Therefore, in this case, f of x turns out to be a linear mapping, which we can write as A times x. Now, the solution to this we can write explicitly. Okay, so one nice thing about linear systems is that we can always write down the solution in terms of standard functions, exponential, sinusoid, polynomials, and so on. And the solution is x1 of t, x2 of t equals some matrix that changes with respect to time times the initial condition vector, which is x1, 0, x2, 0. Okay? And this matrix, time-varying matrix, you remember from 542, is called matrix exponential, and it's denoted by e to the at, a being our system matrix for our LTI system. And if you compute this matrix exponential e to the at for this particular A matrix, it turns out that it's cosine t, sine t minus sine t, cosine t. Okay. Just remember that it was, for instance, you can, one way to compute it is inverse Laplace transform of Si minus A inverse. Okay. In this very simple case, it's actually possible to do it by hand in 2 lines. This computation. Anyway. So that's our state transition matrix, and this matrix is changing with respect to time. That's our initial condition vector. As time changes, this matrix changes, and then this matrix times initial condition vector changes, and all those new points will produce the trajectory or the solution. Okay. Now, we have this mathematical description of explicit mathematical description of solution. Now let's put it in picture, okay? Because we can in this very simple case. So what's the phase plane? Okay, phase plane is this plane x1, x2. x1, by convention, is usually denoted by the horizontal axis, and x2 is the vertical axis, and this is the origin. Okay. So suppose that we start from initial condition where x1 0 is 0 and x2 0 is 1. Okay, so we start from this point. Okay. And then, okay, what's the trajectory? That starts from that point. So that's our starting point. Therefore, initial condition is 0, 1. Okay? x1, 0 is 0 and x2, 0 is 1. Now, that's where we are at t equals 0. And then we start the clock, time starts running, and then this point will start moving somewhere. Okay? Now, let's try to figure out how that motion generates the trajectory. So if this is the initial condition, 0, 1, then we can write explicitly the solution x of t, which is this matrix times 0, 1. This matrix times 0, 1 means that we're talking about the second column of state transition matrix. Okay? So x of t is, therefore, second column, sine t and cosine t. Okay. So that's where we are at t equals 0. At t equals, let's say, pi over 2 seconds. Okay, plug in t equals pi over 2. Sine pi over 2 is 1, cosine pi over 2 is 0. So therefore, at pi over 2 seconds, we follow some trajectory and we reach that point. Okay, so this is where we are at t equals pi over 2 seconds. Okay, if you let another pi over 2 seconds pass, that is at t equals pi seconds, sine pi is 0 and cosine pi is minus 1. So at t equals pi, okay, t equals 3.1415 seconds, we're at that point, and so on. Now, let's connect those points in a reasonable way. How we can do that is look at the norm of this solution, okay? Sine squared t plus cosine squared t, and then you take the square root. Note that for all t, it's always 1. The norm is 1. Norm is 1, and we're using the Euclidean norm. Norm equals 1 means that the distance of the solution at any given time is 1, okay, from the origin. Therefore, the solution must always be on the unit circle. Okay? Therefore, our solution must be circular for this very special linear system. Okay. And then what's the direction of time? Direction of time is clockwise. Okay, so we're moving in that direction. Okay. And we can never, okay, we will always be on the unit circle. That's what this solution tells us. And we can never stop on the unit circle. We always have to be in motion, because there's only one equilibrium point for this system, and that equilibrium point is the origin. Unless you're at the origin, you must always be in the move, okay? And therefore, the solution will be traversing the unit circle for all future time. So this is the trajectory for the initial condition. x0 equals 0, 1. Okay. And this arrow indicates the direction of time. This is where we start, and then as time goes on, okay, t equals 0, then t equals 0.1, 0.2, and so on continuously. Then this is what we do. We always move in circles in clockwise direction. Okay. Now, the family of trajectories use a new definition. Of all trajectories is called the phase portrait of the system. So this is a solution, okay, just one solution, and then tells us something, but it's usually not enough to understand the general behavior of the entire family of solutions. So what we do is we place some other trajectories, okay, along the plane, the x1, x2 plane, and all those trajectories together give us an idea, visually, what's the general behavior of the system. Okay? We cannot put every possible trajectory on the phase plane. If you do that, it will just completely dark, because every point is traversed and it tells us nothing. So what we do is we put some trajectories, a few trajectories, so they are many enough to tell us the general behavior of the solution. Okay? For instance, for this case, for this LTI system, the phase portrait looks as follows for our example. Okay. X1, X2. So this is, let's say, the one that's on the board with unit circle trajectory. Okay, and then if you start from another initial condition, it will again be a circle because it's a linear system. You can scale the solutions, and that's still a solution. That's one nice thing about linear systems. You can scale further. That's also another tiny circle. That's also a solution. And all those concentric circles, each of them make a trajectory, a possible trajectory for the system. And this whole picture together is called the phase portrait of the system. Okay. Now here's one thing that we should keep in mind, that in this x1, x2 plane, in this picture, the information regarding time is partly missing. We only know the direction of time, okay, how the things move as time goes on, but how fast they move is missing, okay, in this picture. In other words, x star equals f of x. In fact, it's also true for the nonlinear case. X star equals f of x, and x star equals alpha times f of x. Suppose that alpha is some positive constant. Okay, alpha greater than 0 have the same phase portraits. So they exactly look the same, phase portraits, x star equals f of x and x star equals alpha x. But if alpha is greater than 1, then this guy is moving faster. If alpha is smaller than 1, then it's moving a little bit slower. But that rapidness information is not embedded in this picture. So you have to write down somewhere, for instance. Okay, now let's move on to something more interesting, namely the pendulum. That's our second example. Pendulum with friction. Okay, so we're talking about this thing, and since there's friction, then eventually it will converge to this stable equilibrium point, which is pointing downward, or if you start exactly at the unstable equilibrium point, then it will stay there for all times. But other than that, except for that very special trajectory, that is the trajectory that starts exactly on the unstable equilibrium point, all trajectories converge to the stable equilibrium point. This we know not by mathematics, but from our experience from the real world. Okay. Now, let's quickly remember pendulum with friction. Okay. This is theta. This is the direction of gravity. Okay? Therefore, this is the stable equilibrium point, and that's the unstable equilibrium. Well, later on we'll be precise about what we mean by stable and unstable, but at least for this example, it's not confusing to use those words because we know more or less the behavior of that simple system. Now, this is a second order system. Let's choose our state variables as the angular displacement and angular velocity. X1 is theta, x2 is theta dot. And the model that we can use is x1 dot equals x2, and x2 dot equals minus, let's say, 10 sine x1 minus x2. Okay, so that's our model. Now, what are the equilibrium points? Okay, recall how we figure out equilibrium points. This is x that equals f of x. Equilibrium points are points such that they satisfy the equation f of x equals 0. Okay, so in this case, equilibrium points, we already talked about that in one of our previous lectures. It's 0, 0, plus minus pi 0, plus minus 2 pi 0. Okay, at any equilibrium point, x2 must be x2 must be 0, therefore velocity must be 0. Therefore all the second entries are 0 at the equilibrium point. And as for x1, it must be an integral multiple of pi, so that sine of x1 equals 0. And integral multiple of pi means that you can have 0 plus pi plus 2 pi plus 3 pi, and also you can go with the negative direction. Okay, plus minus 3 pi 0, and so on. Now, even though mathematically we have infinitely many equilibrium points, but physically, in the physical world, we have only two. One of them is the one that points down, the other is the one that points up. Okay? In a sense, that the odd multiples of pi correspond to the upward equilibrium point, and the even multiples of pi for the first entry correspond to downward stable equilibrium point. So this is outward equilibrium. And these are downward equilibrium. Points. Okay, now how about the phase portrait? So it's not obvious, but it's not that mysterious either once you get familiar with it. So suppose that we obtain phase portrait by performing an experiment or directly using some simulation software. Okay. And it turns out that this is more or less how the phase portrait looks like. Okay. Now let this be our theta dot versus theta. Or x1, x2 plane. This is our phase plane. And now let's obtain phase portrait. So let's mark the equilibrium positions. Okay. First of all the equilibrium points must be on the horizontal axis because at all of them x2 is 0. Okay. This is 0. This is, let's say, pi. This is 2 pi. And let this be minus pi. Let this be 2 pi, minus 2 pi. Now, okay. Now, if you start somewhat close to one of the stable equilibrium points, 0, 2 pi, or minus 2 pi, what's going to happen is, we know from experience that what's going to happen is that it will make some oscillations, and those oscillations will lose amplitude as time goes on, and you eventually converge to the stable equilibrium point. And what happens on the x1, x2 plane is you have this spiraling motion toward the stable equilibrium point. Okay. Things like that. So that's one possible trajectory. And then similarly for this guy, and likewise here, and so on. You're converging to the origin. Now, what happens if you're somehow far from the stable equilibrium point? Okay, for instance, what happens if you start very close to the unstable equilibrium point? You could either converge to left or right, and depending on going to left or right, it means you're converging to this equilibrium point or that equilibrium point. Of course, they are the same equilibrium point, physically speaking, but on the phase plane we obtain different trajectories. For instance, here for this guy, you may have something like this. Okay. Or if you start in the other direction, you can converge like that. Okay. And likewise for this guy. That direction. Then, if you start, for instance, a little bit far somewhere here, so you don't converge to this equilibrium point, but that equilibrium point, and it's something like this. Okay. If you start here, let's say, converge to that guy, likewise. If you start from here, that's one possible trajectory, and here there's another possible trajectory, and so on. And then we have to add these guys here. This is minus 5. Likewise. It's such a motion. And okay, it's not that proper, but we'll have to do it. Okay, so that's more or less it, very roughly speaking. Excluding this has to go in that direction. Okay, and these are going in this direction. Excuse me once again. Okay. So that's the phase portrait, roughly, of inverted pendulum. Okay. Now let's let's once again try to understand what's going on here. For instance, if you start close to the equilibrium point, okay, what happens is you go oscillate, and the oscillations die eventually, and you spiral to the origin. If you start with some initial energy that's quite large, so what you do is you don't converge to that equilibrium point, and then you go once over, okay, from the unstable equilibrium point, and then you start converging. That means here you go over the top, and then you converge, okay. And that's that. And also, how about, there are two interesting trajectories here. Here we have a trajectory that seems to be converging, okay, to the unstable equilibrium point, and here's another one converging to the unstable equilibrium point. How can a trajectory could converge to an unstable equilibrium point? And that's the explanation for that is the following. Suppose that this is the pendulum, and you give it an initial kick, and the kick makes it climb up, but it doesn't have that much energy, so it stays somewhere here and then starts going down and then converge to the downward equilibrium point. And then you now give a little bit stronger kick, okay? Now what happens is it goes up, and once it reaches unstable equilibrium point, it still has some energy, so it goes to the other side, and then it converges to the stable equilibrium point. But between those two trajectories, the one that gets a little bit close but never reaches it, and one that reaches and passes the unstable equilibrium point, there must be a border trajectory such that it climbs. As it climbs, it loses energy, but still it has some energy to climb further, and the climb goes on forever, okay? So this is not actually reaching this point in a finite time. It takes it forever to reach this unstable equilibrium point. These are very special trajectories that converge to the unstable equilibrium point. Okay, now here's a nice exercise. You can think about it first, and then you can verify your outcome by running a simulation. Okay, question. How about the friction in this case? Okay. What happens to the friction in this case? In the friction in this case, we're not converging to the stable equilibrium point, but we do periodic motion around it. And how about the trajectories with high energy? It's something that nice to think about. Okay, so friction in this case. And by friction in this case, I mean x1 dot equals x2, and x2 dot equals minus 10 sine x1. Now that minus x2 term was representing the friction in the original problem. Okay. Now, if we were interested in the local behavior, okay, what happens here, for instance, or what happens here, this is the unstable equilibrium point, excuse me, this is the stable equilibrium point, and this is the unstable equilibrium point, we could have sort of obtained phase vector. If we were only interested in the behavior around the equilibrium point, local behavior around the equilibrium point, we could have used linearization. Linearize the system around the equilibrium point, and then by looking at the eigenvalue locations, we could have set something, perhaps, okay? You cannot always rely on that method to determine the local behavior of nonlinear systems. For the pendulum case, it turns out that it's usable, okay? Now, so what we're going to do is we're going to linearize the system around the equilibrium point, and we'll look at the eigenvalues. Okay. Now, before doing that, let's try to guess the eigenvalue locations. Okay. For instance, here, let me zoom this out. So what's happening is we Okay, for the x equilibrium 0, 0, we have this behavior locally. Okay, and for x equilibrium pi 0, we have this behavior. Okay. Okay, more or less here, and then they're moving away from the origin. Okay. And then, if we consider this as a linear system, what's happening is that we have we're spiraling toward the origin. So that means if you look at x1 or x2 individually, they are sinusoidals, but not sustaining sinusoidal signals. They're decaying sinusoidal signals. And that means that for this case, if this were a linear system, we need some complex eigenvalues, okay? Because of the sustaining decaying oscillations. We need those eigenvalues to be complex, and since they are decaying, they must have negative real parts, okay? And since it's a second order system, all the eigenvalues are there, okay? And we're talking about complex eigenvalues. They must come in conjugate pairs. Therefore, for this equilibrium point, okay, we have the following: lambda 1 and lambda 2. Okay? They're complex conjugate pair. So this is the eigenvalues of the linearization. We're just making a guess by just looking at the phase forward. And how about this guy? Okay. Here we have on a line a trajectory is moving along that line, so that line must be an eigenvector, okay? And here we have another trajectory moving along that line. That line too must be an eigenvector. So we have two eigenvectors, and they're real eigenvectors because we see them on the real plane. Real eigenvectors, it means that the eigenvalues must be real. And how about their sign? This guy is moving away from the origin, therefore this eigenvector must correspond to an eigenvalue with, a real eigenvalue with, which is positive, and likewise this guy is moving toward the origin, therefore this eigenvector must be corresponding to an eigenvalue which is negative. Therefore, we must have a real pair. One of them is strictly negative, the other is strictly positive. Okay. So phase portrait suggests the following eigenvalue locations. For the linearization. Okay, one of them is this, and the other is that. This corresponds to the linearization for the stable group point, and this eigenvalue location corresponds to the linearization around the unstable group point. Okay. X2, X1. And it's easy to verify or refute whether our guess is correct or not. All we have to do is we have the system. All we can do is all we have to do is just linearize the system, obtain the A matrix through the Jacobian, and then check the eigenvalue locations, and that's what we're going to do now. Let's rewrite the system, the original system. x2 and x2 dot equals minus 10 sine x1 minus x2. Okay. Let's obtain the linearization. x equilibrium equals 0, 0. So what's the Jacobian? This is our right hand side, f, so what we do is we obtain the Jacobian. This is notation for Jacobian, and what it means is, it means the following matrix. F1 delta x1, 1 partial x2, partial f2, partial x1, partial f2, partial x2. Okay? And that's what Jacobian is. F1 partial f1 with respect to x1 is 0, because f1 does not depend on x1. Partial f1 partial x2 is 1. Okay. Partial f2 partial x1 is minus 10 cosine x1. And finally, partial f2 partial x2 is, this is only x2 term, it's minus 1. Okay, so that's Jacobian. Now we're going to evaluate the Jacobian at two different equilibrium points. We start with the 0, 0 equilibrium point. Partial f, partial x, Jacobian evaluated at x equals 0, 0 equals our A matrix at this equilibrium point. That is what? Plug in x1 and x2 equal to 0, and this cosine becomes 1, so what we have is 0, 1, minus 10, minus 1. Okay. Now, the eigenvalues. Okay. What we want, what we're expecting is we're expecting a pair of complex eigenvalues with still negative real parts. Okay. And let's see whether the eigenvalues of this matrix satisfy that guess. Okay, the eigenvalues as I minus A, determinant is S minus 1, 10, S plus 1, that's S squared plus S plus n, which can be written as S plus 1/2 squared plus some positive number. Okay. And this being equated to 0, or the roots of this polynomial, by definition, are eigenvalues, and roots of the polynomial are minus 1/2. Okay, the real part is negative, plus minus j 39 over 2. Okay. This is what we expected. We expected a complex conjugate pair with still negative real part. How about the other equilibrium point, linearization at x equilibrium pi 0. Okay. Then partial f partial x evaluated at x pi 0 equals A matrix. In this case we have 0, 1, 10, and minus 1. Okay. How about the eigenvalues of that? Si minus A, the characteristic polynomial reads S squared plus S minus 10 this time. So this is the product of the eigenvalues, and it's negative. It means we have to have a real pair with one minus and the others plus. So it's minus 3.7 and 2.7. Okay. A negative eigenvalue and a positive eigenvalue, both real. This is also what we expected.